All right. Did you figure it out? Are you going to make me happy? Are you going to make me proud? Are you going to make yourself happy and proud? That's the thing. So, are you a NMR expert? Well, maybe not. But are you an NMR intermediate? Maybe so, and that's really what we're after. We just kind of want you to feel comfortable with what you're seeing on the screen and the spectra. All right, so with this particular example problem, C5H10O, we want to know what kind of structure would actually give us something that looks like this. And at first glance, it looks like two major signals. I see one here and I see one there. So two major signals means, look at this, I've got 5 carbons in total. If all 5 of those carbons were different, I would see 5 signals, not 2. So this means that in my head, I'm probably going to have something symmetrical, and my symmetrical mind will go to this idea of splitting the molecule directly in half and creating a plane of symmetry, or a ring system. Now, the ring system, maybe not so much is going to happen here because there's just 5 carbons, not 6, and I can't create this benzene ring. Benzene rings, pretty stable. I mean, that's what we're after. However, this 5 carbons, 1, 2, 3, 4, and 5, could look something like this. Maybe those carbons are all in a straight chain. I don't know. I'm guessing. And we're going to see if this is actually going to match up a little bit later. So with these 5 carbons, I know that only 2 signals are coming from this, which means I'm going to have double ups on these ding-dong types of shifts. So I'm going to kind of go smack dab in the middle here. And this has an oxygen that's present. All right, so I'm going to draw a oxygen that is here. Now, I've got some choices. What I've got here is possibly an OH, because there's hydrogens there. But I also possibly have a double bond O group that could be there, because that's very common as well. This thing could be an alcohol, or it could also be some type of carbonyl compound. All right, so what I'm going to do to kind of fix that situation and the decision right off is I'm going to go back to that chart where it shows me what these chemical shifts are possibly going to be. And it looks like if I had an alcohol group, right, if that is a possibility, I'm going to scan through this chart and I'm going to see OH, 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 OH. Can I find an OH anywhere here? And right off the bat, I see the ROH right there. And it says that that could change, and that's going to change in the realm of 2 to 5. So that is a OH group. All right, so now let's take a look at our example problem that they gave us to see if we have an actual chemical shift between 2 to 5. Now, that's a pretty wide range, isn't it? All right, so here we are. So 2 to 5, yeah, I actually see a chemical shift that happens here. So there's a possibility that that is going to be a alcohol group. I don't know that yet, but it's plausible. I can't just immediately forget about it and drop the shoe on it. All right, now the other option, if this was a double bond O, that would be a ketone, right? So I'm going to go back to that chart, and when I go back to that chart, I'm going to look for a ketone functional group, and we're going to see where that ppm might be located as well. So that will help us make that decision too. All right, so let me flip back to the chart, and I need to find a ketone, just a C double bond O. That is it. That's all that I want. So here is a CH3, CH2, CH2, a methyl group off of a double bond. Now here I see a C double bond O, and then off to the side of that is a methyl group, and maybe on the other side is going to be a methyl group, some kind of R. That is a ketone group there, and that looks like that's going to be a 2.1. So here I see an ROH that can go from 2 to 5, but I also see a ketone that is not variable, and it pretty much hits at 2.1 almost every single time that we have one of those. All right, so does that kind of make sense based on the example problem? And if I flip here, then that is pretty close to a 2.1. It might be slightly off, but that's okay, but it's not as wide of a range as an alcohol group. So either one of these could be okay, but I feel really good about that carbonyl. I mean, it's not a 2.1 perfect match, but it's pretty close. That alcohol group, okay, well, let's try the alcohol group. You know, what if? What if the alcohol group is what it's supposed to be? Okay, well, let's see if that even makes sense based on how many hydrogens that we've got. So if I start smacking hydrogens onto this molecule, I'm going to have 1, 2, 3, 4, 5, 6, and then 7, 8, 9, 10, 11, and 12. There's no way. We only have 10 hydrogens here. I cannot have an alcohol group because I would need more hydrogens in order to make that work and make all of these carbons be satisfied with single bonds all the way through. So then the next question is, well, what if these are like double bonds instead? What if we could have a double bond in here? Can we erase, two hydrogens, maybe one from here and one from there, and create this double bonded molecule somewhere in the structure? Well, if I count the number of hydrogens, if we do that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the hydrogen count works, the oxygen count works, the carbon count works, but let's see where those double bonded kind of protons show up in an NMR. And in order to do that, I need that NMR chart. So here we see double bonds, and that double bond would show up. Well, here is the carbon next door to the C double bond C, and that's not really what we want to look for. What we want to look for are the hydrogens on the carbon with the double bond, and that's what we're seeing down here. These are hydrogens on a carbon with a double bond, and those realms are much higher. Look at this, 4s and 5s. That's what we're going to be seeing if we had double bonded atoms in a molecule. So I would need 4s and 5s in terms of signals in reference to the NMR groups. And I do not have 4 and 5 signals here, which means that the double bonded option is probably not on the table. That's actually not really what we might have. So I'm going to maybe go with my gut, and I'm going to draw the double bond here with that oxygen. Do we have enough spaces for the remaining hydrogens, or do we run out? So let's see, at this point, they all are pretty happy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got 10 hydrogens, we've got 5 carbons, and we have a double bond O. So chemical composition-wise, makes sense. That is plausible structure. And then to make that even better, what we're seeing here is a very symmetrical molecule. I could almost cut that molecule in half, and the half to the left and the half to the right match up pretty well, which means that I can ding dong that one and ding dong that one and not worry about those over there because those were equivalent protons that are showing up, and this leads me to 2 signals that I would see from that molecule. And it just so happens I see 2 chemical signals that's showing up on the NMR. And then I can go through and talk about the ways that this thing is going to split. So the electronegative area is right in here with the molecule. The ones furthest away from that, this is going to be A and that's going to be B, which probably means that maybe this is going to be A and this one's going to be B. That's the order that they're going to show up in. And then for A, if I look at the splitting, next door there's 2 protons. So 2 plus 1 is 3, and that means that A will be a triplet. So this A is happening about a 1, and then that is this one. This is in reference to that very first shift, and sure enough, we see a triplet that matches the predicted thing that we should be having. And then finally with B, which is our second signal, that's going to be the other splitting that they're going to be showing here. Well, next door to that is a carbon with 3, so 3 plus 1 is 4, and we're going to see a quartet. And this is not a double of doublets, because there's just 1 carbon to the left that has 3 protons, and 3 plus 1 is 4. So this is not a specialized quartet of doublets. This is just a straight up quartet that has the smaller ends of the splitting and the 2 higher middles as far as the shift intensity goes. So this makes sense, Everything works out, and that is going to be the structure of what we're seeing in problem 25B. So there we go. Perfectly okay. Didn't take a lot of struggle. We got lucky, maybe, or we could just be that good, right? All right, so now with problem 25C, this is C9H10O2. All right, so C9H10O2, we're going to go through the same kind of thing here, C9H10O2. So if I look at the number of signals, I'm seeing this big one. Oh, and let me go back. Here, look at the integration that they're giving you. They're saying that first signal has 3 that's associated with it, and it just so happens that there's 3 protons on that as well. And then here the integration is 2, and it just so happens that there's 2 protons on that particular shift as well. All right, so again, perfectly matches up, easy breezy as far as the number of protons with that one. All right, so here we see example problem C. And as I was saying with before I kind of got distracted, I see one shift here, I see another shift there, I see maybe 2 shifts here and 1 shift there. So it looks like 1, 2, 3, possibly 4 and 5. So maybe 5 different signals, give or take a little bit. That means that this C9 group cannot all be completely different. There's got to be some overlap. And there's 9 carbons. Some of them are overlapping. This is going to give me kind of the idea that we're going to have a benzene ring possibly. At least that's where we'll start first. In addition to that, the benzene rings normally have signals in the 7s, and we do have signals in the 7s here. So that also makes sense kind of for us. And now we need to kind of build off of this benzene ring. So this is going to take care of 6 carbons for us, and I'm just going to do 7, 8, and 9. We're just going to keep it simple. We'll start there first. If it works, it works. If it doesn't, it doesn't. Okay? All right, so now we're going to build on top of that molecule. It looks like we have 2 carbons, or 2 oxygens here. Oh, okay, so that's something that I didn't anticipate, right? So these 2 oxygens, well, it could be like a C double bond O and an O. That's an option for 2 oxygens here. Or it could be a C double bond O with an OH group separately somewhere else. Or it could just be a C double bond O with an OH group. So I could have an ester functional group possibly. I could also have an alcohol group. And I could also have a C double bond O, and then separately down the line somewhere else, there could be a possible OH group. So a carbonyl as well as an alcohol. If you go back to the alcohol chart, you're going to see a pretty wide range. And the wide range probably fits some of the signals that we're seeing here. So that's not really going to help us make our decision. So we're just going to kind of maybe choose one of them and just go with that. All right, because it's all trial and error. That's what half of this is going to be. All right, so what I'll do is that I'll take a look at this structure and I'll just say, all right, well, what if there is a C double bond O there? And then next to that is the O for the ester. So I still need my 3rd carbon, and that's going to be there. Would I have enough hydrogens to meet the need of everything else that is here? So I've taken care of 9 carbons now, 6 in the ring, 7, 8, and 9. And I need 2 oxygens, and I have those now. They're there. And then I have 10 hydrogens. All right, so 1, 2, 3, 4, and 5. And then the benzene ring would be 6, and then 7, and then 8, and then 9, and then 10. All right, so that works pretty well. Again, it was just a guess. I didn't know if it was going to work. You didn't know if it was going to work in the beginning. You just went along with what I said. So chemical composition-wise, looks pretty good at this point. At least it makes sense from what they just give me straight up as C9H10O2. All right, next up, would this match the signals that I'm seeing here? 5 different chemical shifts, possibly. and then the splitting that they're showing me and they're enlarging on me. If you did some of these other options at this point, like the C double bond OOH, or if you did the C double bond O with an OH separately somewhere else in the molecule, you probably would see that you would run out of hydrogens and carbons would not be happy. It would be a more complicated type of structure for you to work with. Path of least resistance. We'll start there first. All right, so now we're going to ding dong. So if I look at the structure, ding dong, there, ding dong, there, that doesn't have a proton. This carbon, there's no proton. And then this one, ding dong. And then that one is meta, ding dong. And then this one is para, ding dong. And then this is back to meta. Well, it's the same as that one. There's an overlap. And then this one's back to ortho, and that was the same as that one. They're equivalent, so there's an overlap here. So I don't have to ding-dong those two up at the top. So it looks like there's a total of 5 signals based on what I've drawn here. All right, well, that's pretty good, right? I mean, here we get 1 signal and 2 signal and possibly 3 and 4 signal right there. And then here's this last one, which is 5 signals. So the number of chemical shifts kind of match at this point. And then I take a look at what is the furthest away from the electron clouds, right? Or the electron pulls. So the delocalization here is pretty massive, and we get this carbon double bond O as well, that's electron pullers. So I need the furthest away from the ring and the ester group, and the furthest away would be this one, and this is probably going to be that signal there, and beside of that is a neighbor, and this is 2 hydrogens plus 1, which is a total of 3, and if I look at this, this is a triplet. So therefore, that makes sense. At least it makes me feel good because that does match up pretty well. And then the integration number actually perfectly matches the number of hydrogens that we're getting here. Again, those calculations are already taken care of. We've talked about the integration calculation a little bit earlier, but here they're kind of already taken care of me. All right, so that, pretty good. And then we go on to the next closest one with all of this mess with the electrons. And this would be here at that spot. So that would be C. And it looks like that this possibly would be B that's here. And that is 2 carbons. I'm getting a different shift. We've already said that. And then next door is 3 plus 1 is 4. So we're getting a straight up quartet here. Again, not a double of doublets, but a straight up 3 plus 1, which is 4. And what I know it's not a double of doublets because that one and that one is smaller in height than the 2 in the middle. So that means it's probably coming from something like a CH3 group. Not only that, look at your integration number. That integration number is matching pretty well with those 2 hydrogens that are on that particular carbon. All right, so that makes me feel good as well. The other 3 that's on the benzene ring, those are different signals. I see that there are different signals there. I kind of was iffy about those 2 that are nestled together pretty close, but they probably are separate. I can't go in. I can't actually see how those are splitting up. And because of that, I don't want to go through the whole calculation of calculating the splitting or the multiplicity of those shifts. However, look at this. I see a 2 and a 1 and a 2. So what that means is that here in the ortho positions, those would be 2 equivalent hydrogens. Here in the metas, those are 2 equivalent hydrogens. And then here on the para, that is 1 equivalent hydrogen. And I would see a 2-2-1 there. And I see a 2-2-1 here from that benzene ring. So once again, it makes me feel really good that this possibly is the structure of that NMR that we have. All right. All right, next up, we get an example problem that looks like this. I'm not going to do any more of these, right? This is something that you can do on your own time. A through P, they're just example problems. Some of them we've done already, some of them that we haven't, but it's just the rehash of everything that we've done. Describe the NMR spectrum. So what they want you to do here is calculate the number of chemical shifts, go in, talk about multiplicity, go in and maybe talk about doublet of doublets and those types of things if they're happening, and just describe how the NMR would look based on these chemical structures that you see. So A through P are just example problems for you. That's all that they are. And you can do these on your own time. I'm not going to do them for you. However, if you do want answers to those, I want you to pause the video, try these on your own, and then compare them to an answer. And those comparisons can happen here. So these are the example answers to A through P. All right, so once again, pause the video, match it to what you did, and see if they are exactly the same. And if not, where's the problem? Where did you go wrong? And that way you understand your mistake and you know not to do that mistake all over again. Okay? All right, so with that said, I'm going to actually stop the NMR videos at this point. We can go through coupling constants. We can actually go through a couple of other things that we can talk about: carbon NMR, coupling constants, more about the calculations and those types of things. And I'm just not going to do that right now. So if you see another lecture video folder that appears, that's what you will find in that lecture folder. And it just depends on the type of mood that I'm in. Do I think that carbon NMR is going to be important for you? If so, I'll make it available. Do I think that these other kind of more detailed, in-depth discussions of NMR is necessary? If so, I'll open up that folder for you. However, I do want you to be left with one more example problem, and that's something that looks like this. And these I love. Okay, I'm going to say that again. I love them. Especially on things like a final exam or on an NMR test, because it makes you go back and dig out the infrared that you should know at this point. But this is actually blending infrared with an NMR problem. So if I look at this example problem, it says identify the compound with the molecular formula of C9H10O that gives the infrared and the HNMR in the following problem. So this is very similar to the other two example problems that we did. However, they're giving you an NMR to make your job a little bit easier. Because remember, we were like, is this a ketone? Is this an alcohol? Is this an alcohol plus a carbonyl? What kind of functional group is it? I don't know. That's kind of the decisions that we were going through at the time. This infrared is going to tell us what functional groups that we have. So keep in mind, in that previous example problem, one of our options was a full up alcohol group. What if I gave you an infrared and I said, use this to your advantage? I would look at that infrared and I would say, well, this can't be an alcohol, because if it was an alcohol, it would have a dip that looked like this. So I know that I can throw out the alcohol group. And then our other choice was carboxylic acids, C double bond OOH. Well, this is not a carboxylic acid, because I know if it was, it would have this little jaggy little thing down there at the bottom, and we don't even have the big dip. So that would completely eliminate those options from the table. Infrared actually makes your job easier, not harder. So as long as you know how to interpret infrared, it makes the NMR functional groups and the foundation of those chemical structures a little bit easier for you to kind of navigate and start with not a trial and error full blown up, but at least a really good guess about what you have. So for instance, C9H10O, well, okay, I've got an oxygen, 9 carbons, so I'm going to have probably a benzene ring here, and then off of that was those 3 carbons, 1, 2, 3. And then it was this idea, well, what is the O group? All right, well, if that O group is an OH group, the answer is no. The infrared doesn't show me that it's an OH group. So what other functional group do we have that actually takes into consideration this kind of oxygen functional group? Well, you're going to look at this and say, well, I know what that would possibly be. That would possibly be in the ketone family. So do we have an aldehyde? What if it was at the end? Well, 27 and 2800 would be the aldehyde. So up here, I don't really see the double jagged little bunny ears for the aldehyde. So it's not an aldehyde functional group. It can't be one of those either. So I know that this double bond O can't be at the end. So maybe the double bond O would be somewhere in the middle. This is the concept of how we can use infrared to help answer the NMR questions. Then when I feel good about what I've done based on infrared functional group, I then go to NMR to see if it matches. Do the chemical shifts match pretty well? Do they not match? Is there something that I've got to do in order to make this work a little bit better? Keep in mind though, look at this. Here's the 1700 peak. So that means a C double bond O definitely has to be involved, but it can't be an ester, because that's going to be another oxygen that I don't have in the structure. So that eliminates the ester group. I already know it can't be an aldehyde because we don't see that OH or the double ears at 27, 2800. I know it can't be a carboxylic acid, and that's because I don't see an alcohol group. And this is going to start to narrow down your decision of what the structure can actually be. So if you took a look at this infrared, and if you took a look at, okay, I've got a C double bond O group, that is a ketone, and then a possible benzene ring on this thing that's going to give rise to possibly 3 different signals. I'm going to flip to this NMR, and I'm going to say, does that really match what we have? Well, this looks pretty much like the benzene cluster. Right, it happens in 7s. I see a 2-1-2, and that was kind of traditional of what we saw in the other example problems with the ortho, meta, and para protons. And then it looks like I've got 2 other signals in place. So we need to go through and see if it matches with the signals, if it matches with the splitting, and so forth. All right, here's another example problem that just takes that message home a little bit more. And I will say that this is not the answer to the question. So if you're doing this, this is not it. And I want you to prove to yourself that this is not it. Okay? Only one other option that I can put that C double bond O. Try that option and then see if that matches. All right, problem number 30, same thing here. I'm giving you an infrared. This infrared's giving you information about what we have functional group-wise. And then here's the NMR. And that NMR is going to tell you all about the signals and all about the splitting. Once again, use the infrared to figure out what you have functional group-wise, and then narrow down your choices, and then use the NMR in order to confirm what you actually did. All right? Okay. So just another kind of side note on the NMR here. We can talk about resolution, and resolution is like MS. It's all about the chemical shifts and if they can separate the chemical shifts from each other. So this is an idea of resolution. The more expensive that your instrument's going to be, the better it can separate these chemical shifts from each other. So more and more and more expensive as we go from bottom to top, and you can see how it cleans up the splitting. You can also see how those chemical shifts are separated from each other, and it's all about the magnet there. All right, so the better the magnet, the more expensive that instrument is going to become. And then finally here is just the idea that we can also do carbon NMR as well as hydrogen NMR. And what we would do with carbon NMR, it's actually much cleaner and much simpler, but we would just do what we've always done with hydrogen, and we would look at this and say, how many different types of carbons are there? Not protons. And we would see 4 different types of carbons, and we would see 4 signals that come from those types of carbons. And we don't really go through this idea of splitting and those types of things, right? Notice that here with carbon A, well, it's got a next door neighbor, and that's 1 carbon that's next door to it. And I don't really have to go into the splitting concept. And if I look at the signal, it is 1 line pretty much that goes straight up and straight down. Then if I take a look at B, the same thing, that B has one carbon that's next door. And if I look at that signal, I see one signal pretty much straight up and straight down. If I look at C, well, we've got a carbon to the left and a carbon to the right, but I don't really talk about signals either. And then if I look at D, well, I get a different carbon to the left and a different carbon to the right, but once again, I don't really talk about signals. So carbon NMR is much simpler because each one of these signals basically is giving you an idea that these are the number of different carbons that might be present. So you can use carbon NMR as well as hydrogen NMR on the same molecular structure to help confirm your decision even more. The problem is that we don't really start with carbon NMR because it's very hard to deduce chemical structure here, just on it alone. You can't really pick out what the structure is based on just the different types of carbons that there's going to be present. I don't know about the hydrogen numbers. I don't know anything about the neighbors. I don't know anything about the splitting. I don't know if I'm ordering them up the right way. Only thing that I can take away here is that there's 4 different types of carbons and that's it. That's all. So we will often not talk about carbon NMR for that reason, and that's why we focus on hydrogen NMR instead. But please note, and I can give you those types of problems, here is a carbon NMR and here is a hydrogen NMR. Use these two things to your advantage. And carbon NMR will help confirm how many different types of carbons that you have, and the hydrogen NMR will help you confirm how those carbons are actually connected to each other. Finally, once again, like we said in the very beginning of the lecture series, the NMR is important because in the medical world, this is known as MRI. The reason that they changed the name is that the N stands for nuclear, and a general consumer or a general patient that's out there in the hospital, they do not like the word nuclear because it makes them think of mushroom clouds and blowing things up. So instead of the word NMR, we use the word MRI, which is magnetic resonance imaging. So we just take the same instrument pretty much. You are the sample, not an actual organic compound, and you are slid in to an instrument that runs off of a magnetic field. And when that runs off of a magnetic field, you are injected with dye. And those compounds, attention, line up. And then we start clicking the magnet. Boom, 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 boom. That's what we do. So what you're seeing is that there's very high powerful magnets all around this tunnel. And those very high powerful magnets make your molecules line up in the magnetic field. And then we start this pulsation of the magnetic field. And that magnetic field will drastically increase a little bit over a course of maybe 45 minutes to an hour, depending on how long that you're in these systems. And then the way that these molecules kind of scream, and then get picked up by the detector. If it picks up by the detector, it can determine how deep inside that these compounds have came from, or that the screams have came from. And what you begin to see on the computer screen is an image of what's on the inside. So it looks at how it's reacting with the magnetic field. It basically looks at how long the system is taking to respond and how strong that the signals are that's coming from the instrument, and it's generating this image that you're seeing on the MRI computer screens when they begin to do these imagings of patients, and maybe in a hospital setting and so forth. Maybe they need to see what's wrong with your kidneys or your liver or some type of tissue, and that's the purpose of the MRI, right? right? X-rays are more for bones and hard things like that. But if you want to know more about tissues, then the X-rays really aren't going to do it for you. You need some type of imaging device like MRI in order to do that with. So MRI is just really an NMR. That's all that it is. It's not in a chemical laboratory space. It's in a hospital type of setting. It's all based on your water molecules that you have in your body and some dyes that they can inject into you when they begin to do the imaging that they see from here. So that's basically the story of MRI. And if you are going to med school, or if you're taking this because you want to be a physician's assistant and so forth, you will very often say, why do I need to know this? Why do I need to do this? Well, ding dong, I want you to know that MRI is NMR, basically what we've went through, except it's just a different perspective. We're not doing it in terms of the medical community, we're doing it in terms of a laboratory community. And what works in our lab works in the hospital laboratory setting, which is just basically an MRI imaging office. All right, so with that said, congratulations. You can go now and go next door, maybe 2 doors down, get a drink, have a party, and from this point, I wish you luck on NMR. All right, so that's it for me with nuclear magnetic resonance, and we can go into more detail than what we did, but I think that we kept it as clean as we could and as basic as we could. Basic. Did he just say basic? And I did. So that's basically what NMR is all about. So good luck with the example problems. Good luck with the online assignments. Good luck with the test information that shows up on this test. But just like with IR and MS, you cannot Google these folks. You can't do it. I want you to stop Googling answers because it's not working for you at this point, and it's not going to work with you continually in the future. So you have to learn the procedures, you have to learn the methods, and then apply those techniques to these example problems, because there's no way on earth that you can take something like this and Google it and give me the answer on the test or an assignment. If so, good luck to you. You got lucky. I need to take you to Vegas. We need to bet some money on a table. All right, so again, you know how to get a hold of me. Final video, possibly of NMR. And if I do want to go into more detail, depending on the year, depending on the trends of the NMR technology, then we'll open up another lecture module folder that you can go into and finish out those remaining assignments. But otherwise, sayonara, folks. It's been good to know you.